I am Brenda Leong, the Senior Counsel and Director of AI and Ethics at the Future of Privacy Forum, and I would like to welcome you today to this session. FPF is located in Washington, D.C., although of course most of us are not working in the office there now. And we have a globally dispersed staff working on consumer and commercial privacy issues around the responsible use of data for emerging technologies. The Digital Data Flows MasterClass series is an 8-part program hosted by FPF and the Brussels Privacy Hub, an academic research center at the University of Free Brussels. Our goal has been to present a series of academic classes that are free and open to the public on technical subjects that are of the greatest interest to lawmakers and public policy experts, specifically those technical topics that have implications for privacy and data protection. In other words, we don't spend much time on what the law is or even what it should be. Our goal is to teach the technical and conceptual basics of what policymakers might need or want to know in order to consider the best legal and policy solutions. We've covered a wide range of topics that you can see here on the slide, and all the classes in this program can be found archived at fpf.org/classes. Although today's topic, blockchain, is the 8th and final class in the series, FPF will be continuing to host standalone sessions just like this on technical topics in the future. If you have an idea for a topic you'd like us to cover, send an email to info@fpf.org, or if you'd like to receive updates for future events, please join our listserv at www.fpf.org. Today's session is being recorded, and we will be tracking questions in either the chat or the Q&A functions. So please post your questions as we go, and we will do our best to include them all and respond either during the sessions or at the end during the Q&A. I will be leading the first introductions, and I will be joined later by Dr. Rob Van Eyck, FPF's EU Managing Director. I'd like to introduce our other speakers for today. Jake Vanderland is the Chief Information Officer and Director of Information Technology and Regulatory Informatics at the New Brunswick Financial and Consumer Services Commission in New Brunswick, Canada. He was previously its Director of Enforcement, a position he held for 12.5 years, and he is a regular speaker and teacher with respect to emerging technology-related issues, particularly in the context of financial services and consumer protection. Dr. Matthias Arzt is a senior legal counsel at Deutsche Bank AG since 1999. He has been practicing data protection law for many years and was particularly involved in the implementation of the GDPR within the Deutsche Bank AG. Matthias is a regular speaker on various national and international conferences, seminars, and webinars, and the author of numerous articles on data protection. Specifically, our two speakers today were involved in the publication of the Handbook of Blockchain Law, published by Wolters Kluwer, of which Dr. Arzt is the co-editor and co-author, and Jake Vanderland authored the first chapter called Understanding Blockchain. So with that, I think we know we have some very expert inputs for the day, and I'm going to turn it over to Jake to lead off the first sessions. If all of our other speakers could please turn off your video.
Wonderful, Brenda. Thank you so very much for that kind introduction. So just a couple of preliminaries. My email is there for anyone who wants to reach out afterward. LinkedIn, feel free to connect if you like. Couple of preliminaries with respect to the disclaimer for this session. Any opinions I express are my own and not my employer. I don't endorse any of the products, websites, what have you, that I'll be referencing. It's my intent here to explain how blockchain works and not to advocate for it particularly. So what we're going to cover today, I'm going to try and cover these 5 things in the next 40 or so minutes in the hope that we'll have a little bit of time to ask or to respond to questions. So we'll talk about and spend most of our time talking about how a blockchain works, and then we'll dig into the various types of blockchains. We'll look at the most successful incarnation of blockchains, cryptocurrencies, and then I'll delve into the second most successful incarnation of blockchains, which is the platform-based blockchains, including Ethereum. and then a little bit about smart contracts, which is really what Ethereum offers to the mix. So I get asked regularly to explain blockchain, and I think I've spent the last 3 or 4 years in various venues doing that. But to sum up what a blockchain is, I think we should think of it in the context of a record-keeping log. It really is nothing more at the end of the day than, to put it bluntly, an append-only transaction log. So a log that you can add to at the end that is a record of something that you want to keep track of. And the core idea that blockchain tries to address is record keeping. It really is a record keeping device. And of course, as humans, we've been record keeping for thousands of years. We keep track of entitlements to goods that we've purchased or sold, bills that need to be paid. Banks use record keeping systems to track account balances and loans that are due, etc. So record keeping is really quite integral to our society and has been for many years. And the systems we use to rely on for record keeping are, of course, very, very important. So think of it very much in the context of blockchain as a record keeping device. That's really its core functionality. So I'm going to explain blockchain by way of reference to the most popular blockchain, which is the Bitcoin cryptocurrency, and how it works. Bitcoin came to the fore in around 2009, which is 11 years ago, maybe surprising to some of you, but we've actually had blockchain for some time. So Bitcoin, as you'll see, was the first one, and it really brought together a bunch of different technologies in a very innovative and clever way to create the kind of blockchain that we have today. So let's dig a little deeper into Bitcoin itself. I suspect many of you on the webinar have bank accounts, and every month or so you get a statement from your bank that articulates the deposits to your account and your withdrawals from your account. And you may take some time to reconcile that statement with your checkbook, or you may just put it in a drawer somewhere on top of the ones from last month. So you have in your house a stack of statements, presumably from the bank, that reflect, your entitlements and your withdrawals and your expenditures and your income for a particular bank account. The actual record, the final record keeper of all of those items, however, is your bank. And the bank keeps all that information in a centralized location, usually duplicated and backed up, of course. But at the end of the day, the bank is the final arbiter of the correctness of your statements. And you have, of course, perhaps an obligation to verify that the statements are correct, and there are mechanisms in place to correct them if they are wrong. But at the end of the day, the bank keeps in a centralized location the final arbiter copy of the bank statements for your account. So what blockchain does is kind of flips that on its head and adopts an approach where that is not stored in one central location, but we in fact store that stack of statements, that chronological ledger of transaction, on multiple computers on the internet. So we have, instead of one centralized location for all your bank statements, a distributed network of copies of all these statements on a network that is connected together on the internet. And in the case of Bitcoin, that network size is thousands of computers. Now, as you look at this, you should perhaps have some questions. One of the questions that should come to mind is, how do you make sure that all these ledgers are in sync? How do you ensure that a ledger stored in the computer in South America is consistent with the one that you stored in Spain? What mechanism is in place to prevent things like double spending? And double spending is effectively spending an entitlement twice, taking advantage of perhaps a delay in the update of the ledger. So your ledger in South America might be up to date, you still might be able to spend it again on the ledger in Spain if there was no effective reconciliation or updating mechanism. So that is the crucial question and challenge that the blockchain, the Bitcoin blockchain, was able to solve. So let's dig a little bit deeper then into this blockchain. What is it and how does it actually achieve that outcome of synchronized ledgers on thousands of computers across the globe? I want you to think of a blockchain as a train. And the train is just like your statements in your desk drawer, a chronological series of transactions that are glued together. Every wagon on the train has transactions in it. The ones at the head of the train have the earlier transactions. The locomotive has the first transaction, like your deposit into the bank perhaps. And the last wagon on the train has the latest transactions in it. So here's another look at that analogy. So as you can envision, blockchain has a mechanism which allows us to lock down each of these wagons in this train in such a way that we can't, after the fact, change them again. So we can go back into the train and look at all the wagons and have comfort that the transactions that are in these wagons are all unaltered, that they're all still the same as the time that they were added to the blockchain train ledger. So how is that done? Well, in order to kind of appreciate that, it's important to do a little bit of math and talk about a particular mathematical function called the cryptographic hash function. All of you, I'm sure, have gone to school, have had math, and are familiar with what a function is. You know, the old x squared plus 9, 2x plus 4, what have you. And a function really is just a way to transform data, right? So if you have x squared plus 9, you put in any x and out comes something else. So if x is 1, you get 10. If x is 2, you get 13. So a hash function is a similar kind of function. It's a bit more complex. It's not just 9x plus 2. It's a longer function. It's more complex, and it does a bunch of things in sequence. But at the end of the day, it still takes an input of some sort and then renders an output. Now, a cryptographic hash function has some very unique properties that are very valuable in solving the problem that blockchain solves. So the first thing that cryptographic hash function offers is the unique digital signature property. So with a cryptographic hash function, we can put in a very large file, or text file, or anything else that is able to be digitized, run it through the hash algorithm, and come up with a hash value. So the output of the hash function generates a hash value. And the key feature of that hash value is that it is unique for all the various inputs if you have sufficiently structured data as inputs. So let me offer a bit of an illustration of that. So here is on the left-hand side some inputs, our cryptographic hash function in the middle, and then some outputs on the right. So as you'll see in line 2, we have the white rhino runs into the hungry hippo, and on the right you'll see the little hash digest or hash output or hash. And then we've changed one letter on the third one, where it now says into, a typo mind you, but nonetheless, you'll see that the hash digest or output on the right-hand side is completely different. So that is the feature of these cryptographic hash functions. And the value in this, in that even if you make the most minute change in the input value, you will have an immediate, dramatically different output value, is very valuable. And we use it all the time. If you download a file from the internet with a particular program, many of these will do some hashing to verify that the file that is sent is the same as the file that is received. And the way that's done is quite simple. You run the initial file through the hash function, out comes a digest. You transmit the file to the recipient. The recipient runs the file through a hash function. And if those two hashes are the same, if those two outputs are the same, then we can be certain that the file has not been corrupted, changed, or altered, that in fact the file is the same. So that is one of the critical features of these cryptographic hash functions that are being used in blockchains. The other important aspect or nuance to appreciate is that a cryptographic hash function value is not reverse engineerable. You cannot take the hash value, which is usually only about 70 characters long, and reverse engineer the original text from it. So that is an important aspect of it. Well, of course, it's also something that we use in cryptography in general. So the hash function, in short, offers us to create digital signatures of text or files that will confirm that the file has not been changed. So how do we then apply that in our train analogy? And the crucial kind of insight that I think you want to take away here is that we hash the contents of a particular wagon and use that digest value in the next wagon. And the way it's done is you actually embed the hash digest of one wagon into the text of the next wagon. So here's a bit more detailed illustration of that aspect. So as you can see, by incorporating the hash value from block 23345 here into the text that's going to be hashed for block 23346, we're immutably tying these blocks together. If there's any change in block 23345's transactions, we're going to have an immediate change in the digest, and it will no longer match the digest in the next block. And we can then be certain that there's been some change in block 23345. We can even go deeper and actually find out what that change is, because the transactions themselves within the yellow block here are also organized using this kind of hashing process. All the transactions are hashed together, a hash is calculated, and then two other sets are glued together and so forth in a Merkle tree arrangement. And if you want to know more about Merkle trees, I won't dig into that here, but our book covers that in some degree. Suffice it to say that we're using the cryptographic hash function here to tie together subsequent blocks of transactions by forward embedding the hash values in the text that's going to be hashed in the next block. And here's a bit more detailed illustration of that. And as you can see here, I've embedded an actual hash value, some transactions, run it through a cryptographic hash function, and then inserted that hash back in the top of the next wagon or block. So that is, in a nutshell, how we tie those wagons together to form this immutable blockchain. But that's not the end of it, because there's a slight problem. You know, with computers these days, we could, if we wanted to, recalculate the whole blockchain. We could go into an early block of the train and make a minor change, and then just recalculate everything if we had the sufficient power and control over all the different versions to reconstitute a blockchain in a way that would allow people to manipulate the data. So the critical question that blockchain, and particularly Bitcoin, solved was how to prevent that redoing of the whole train very quickly. And the key concept here is the addition of what is known as a proof of work. And proof of work is what we're going to do here is really add, in essence, a cost to the addition of a block to the blockchain. That every time we add a wagon, there's in essence a 10-minute cost that we're imposing to that addition process in order to prevent someone else from redoing the whole blockchain later. And that time cost is achieved through this proof of work process. So let's dig a little deeper into how that works. So what we're doing in the proof of work process, we're adding another feature to the process of this confirmation and hashing sequence by adding a nonce. And a nonce is just a mathematical term for a number used once. A nonce is usually some sort of variable that we can increment and reuse with an incremented value in a particular equation. So the way that the nonce is used is we change that nonce every time we hash the block of transactions in the previous digest. And what we're looking to do is we're trying to find an output dash digest that is below a certain value. And why do we want to do that? We want to do that because Mathematically, if we set a certain threshold in that the digest for a particular hash function output has to be below a certain value, that will dictate an amount of time required before that particular item is found. It's a statistical probability calculation that determines that we need to run this hash by changing that nonce so many times that after 10 minutes, we're highly certain to actually get an output. So what we're actually looking for with this hash digest for every new block we're trying to confirm is a value below a certain amount. So here's a traditional hash digest output that you might find in a Bitcoin blockchain hash function output. But what we're actually looking for is a hash digest that starts with a certain number of zeros, 14, 15, 16 zeros. The idea being that we're trying to find a hash digest within a subset of all the ones that are possible, which we know with the hashing computational capacity that we have will occur after a certain amount of time. And we can manipulate the size of that number below which the hash digest must fall in order to determine the difficulty given the computational resources available. So in short, what we're doing, we're not just doing the hash function once per block, we're doing it repeatedly, millions, trillions of times until we find that particularly unique hash below a certain value. And that, on average, takes about, with the current configurations, about 9-10 minutes in the Bitcoin blockchain. So here's just a quick overview of that mining process, as that is known, which is the process of adding that nonce, incrementing it, running it through the hash digest, and looking for that hash value below a certain threshold. So that takes about 10 minutes and is done on all the different computers connected to the blockchain network. Each of the nodes on the Bitcoin network takes a set of transactions, puts them in a bucket, adds a nonce, adds the digest from the previous block, and hashes that until it finds this magical hash value. So it is, some people describe this as a puzzle. It, to some degree, I suppose, is a puzzle, but it's the same puzzle every time. We're just looking for a different answer, a different hash value each time. You know, a hash value that has to meet certain constraints, but it's really just the same thing over and over again. So what happens once a particular node on the network, after having taken a bunch of transactions and hashed them like this, gets a hash value that is below that threshold? Well, that is considered to be a winning hash, if you will. And what happens then is the following. So as soon as one of the winning hashes is found by a node, one of the thousands of nodes on the network, it sends a message to all the other nodes on the network and says, I have found a hash that meets the requirements. Here it is, and here are the transactions that I'm thinking to confirm. Please check them. So each of those computers will run through that set of transactions in the hash digest once. It only has to do it once to confirm that's correct. So it's very quick. And once 51% of all the nodes on the Bitcoin network have accepted the block, it is considered to be confirmed and is then glued on, if you will, as the next wagon on the blockchain train. In addition, the winning node, the computer, if you will, or the group of computers that identified this winning block gets a reward. They get an entitlement of currently 6.75 Bitcoin that is embedded in the winning block that they've added to the blockchain. And they can then spend that as they see fit. So that, in short, is how the core functionality of blockchain works. It really is nothing more than a repetitive application of the cryptographic hash function with this proof of work layered on top that enables us to prevent the change of all the data that is stored in this log previously. And that is certainly the innovation that Bitcoin offered. So let's look at cryptocurrencies now as the use case that have applied blockchain first and continue to be the primary use case, certainly, as far as public engagement is concerned. So the first cryptocurrency, as I mentioned, was Bitcoin. It was really a culmination of ideas that came from the late 60s and 70s, very much enabled by innovations in public-private key encryption, as well as the internet. It's interesting to learn about the history of Bitcoin because it really is not uncontroversial. It's very much rooted in a kind of cypherpunk mentality, as it's known, which is a general distrust in the establishment and banking and a desire to be free from government and from control. So much of that animus is still very much present in the crypto space, in the crypto ecosystem, and you'll see it if you explore it. Many of the evangelists in the cryptocurrency space continue to tout these cryptocurrencies and Bitcoin in particular as revolutionary products that are intent to enable complete freedom from government and the establishment. It's interesting to note that Bitcoin, when it was first brought to the fore in 2008, as you can see here, this is the email from Satoshi Nakamoto, the unknown creator of Bitcoin. We still don't know who Satoshi Nakamoto is or whether it's one person or many people. Mr. Nakamoto, or maybe Miss Nakamoto, continues to have a significant entitlement on the Bitcoin blockchain that has not been touched for many years. So there's some suspicion that perhaps he or she is no longer with us, but that is still not the final answer to that question. Note in this email that Satoshi refers to an electronic cash system. And really, Bitcoin hasn't yet, and perhaps it may not, succeed in that elusive goal because I suspect many of you are aware, Bitcoin is not being used as a means of cash in today's society. It is more of an investment scheme. People buy it to speculate in the hope that it will go up in the future. I won't delve into that further, but interesting to see that whole ecosystem evolve. There are those who say Bitcoin is the world's largest Ponzi schemes, and others say it's the next greatest thing since the printing press. So we'll see what happens. A couple of things about how cryptocurrencies work that I suspect you may already know, but I want to just quickly point out. Transactions on the blockchain are not authorized by name. They are done using public and private key encryption. So all the transactions that are recorded on the blockchain are referenced to their owner by their public key, and an owner can effect transactions using their private key. So the effective owner of any entitlement on a blockchain is the private key, and it is that must be guarded, because if you have the private key, you in fact have full control and ownership of any entitlement on a blockchain. There currently are well over 700 active cryptocurrencies in play. We've seen a number of them move on, but there still are a few that have persisted. Bitcoin has been around since 2009-ish or so, as I mentioned. Many of these cryptocurrencies are now being created on top of other cryptocurrency platforms, and we'll talk about that in a minute. You may also have heard recently a discussion about digital currencies at the government level. China, in particular, released a central bank digital currency, the digital yuan. I should note that particular currency does not use a blockchain. So some people suggest that these kinds of evolutions are an indication that blockchain is on the cusp of breaking through the banking system, but that should be tempered somewhat, I would submit. A couple of other things about blockchain implementations beyond blockchain. We have many different ways of adding that cost confirmation that we've talked about in the Bitcoin blockchain. There are ways of doing that using various voting mechanisms, proof of stake, Byzantine fault tolerance. There are also DAG-based, directed acyclic graph-based cryptocurrencies that are available. These are not blockchains in the traditional sense, but they adopt some of the methodologies of blockchain. An interesting incarnation is proof of elapsed time, which actually uses a hardware solution created by Intel to create this cost function. Much more on that in our book. I really don't have time to dig deeper into that now, but by all means, go to our book. The first chapter, I should note, is available to read for free on Google Books. So you can just Google the title, and the whole free first chapter, which is the technical one, is available to read there if you want to dig deeper. Two primary classes of blockchains now available: public permissionless blockchains, and those are ones like Bitcoin, where anyone can contribute to the blockchain by starting a node, anyone can submit transactions, and anyone can participate in the confirmation process. There are private blockchains as well, which require a permission process. So there is a limitation on who can participate, who can contribute transactions. Any of these permission blockchains do not have proof of work confirmation processes. They use something different to create that immutability of past transactions in the log. More on those as well in our book as well. So I want to briefly conclude by talking about blockchain as a platform. So in addition to Bitcoin, which just stores transactions, there's a whole class of blockchains that store other things as well. So you can not just store transactions, you can also store code, and that is really how blockchain as a platform is used. So the features of platform-based blockchains are they still track transactions very much the same way that Bitcoin does, but in addition to storing transaction data, they also store computer code. So that computer code can be called, can be executed, and with that code, the state of certain variables also stored on the blockchain can be changed. So you can inject logic inside the blockchain that is immutable, that becomes, in essence, unchangeable and predictable, assuming you've written the code correctly, of course. So the Ethereum blockchain uses the Ether cryptocurrency for tracking entitlement. It also has another currency called gas, which is used to pay for the running of computer code on the blockchain. You can appreciate that some computer programs may run forever. So in order to limit that, there is the requirement to submit gas with a request to execute code, which then, once the gas runs out, stops the computer code from running. The Ethereum blockchain has a much shorter confirmation time. It's about 15 seconds. And this code that's embedded in the blocks on the blockchain enable the creation of dApps, distributed apps, which leverage these states and variables that are stored on the blockchain. So you have an external application that looks to the blockchain for the critical data that it uses. So smart contracts, really, I've already kind of touched on what they are. Smart contracts are just code, logical mechanisms stored on the blockchain, which allow the state of certain entitlements variables in the blockchain to be changed by calling these contracts on the blockchain itself. And the vending machine is a perfect example, a very simple example of the kinds of logics that you could embed in a blockchain. Here's a kind of the decision workflow that you might deal with that you would see in the case of a vending machine, very similar, and you could very easily create this kind of functionality on the blockchain, where you have different states and values that contribute to different types of paths through a decision tree like this to generate outcomes and state changes of variables on the blockchain. The primary use case of these types of smart contracts to date, and there are many, but the most popular one has really been tokens. So tokenization of any of a number of things. I don't have time to dig into tokens. Our book covers it in some detail. But again, tokens use these kinds of contractual code bits in the platform in order to track entitlement to anything from securities to artwork to what have you. Here's a sample contract that from the Ethereum platform that simply, once implemented, is able to generate a token like the one I've referenced. I'll conclude with the most popular smart contract to date, and it's not what I suspect you might think it is, but the most popular smart contract to date has been CryptoKitties, which is a game that allows anyone to create digital cats on the Ethereum platform. Very popular in 2017. In fact, when it launched, it was very much a test of the Ethereum platform because it almost ground it to a halt given the volume of transactions that were being submitted. Interesting ecosystem, the CryptoKitty ecosystem. There are cats. I think the cat that sold for the most was in May of 2018. There's a digital cat out there that sold for $140,000 US. So a couple of insights from CryptoKitties. You know, the actual logic behind CryptoKitties is really quite simple, but it certainly did demonstrate some of the barriers to these kinds of platforms with respect to the logic that it was capable of supporting. And you know, those challenges persist, and there are innovative thinkers who are trying to address those. But smart contracts are evolving, and certainly we're seeing some more useful applications of smart contracts coming to the fore. So that's my short and certainly high-level introduction of what a blockchain is. I've given you some insight, hopefully, into how it works, and that is the end of my session. So I think I'm not sure if we're doing Q&A now or if we move on. I'll look to Brenda for some insight here.
Yes, thank you. Sorry, I'm getting a little feedback. That was a great overview of blockchain. I'm sure raised a lot of questions as well. And so we'll address a couple of those. I have a couple of general questions I want to lead off with. We will have to be quick since we're only going to take a short Q&A session for now, but we will also have a longer Q&A at the end. So if you have questions, I see there's already one in the Q&A, please post them. And if we don't get to them all right now, we will try to get to them later. So Jake, you've given us a lot of information about how blockchain is used, the things it is doing and doing well in some cases in terms of its original purpose of cryptocurrency and things like that. Can you also sort of be the devil's advocate and say, what are some of the things that maybe it is not doing as well, or that it's being touted as a possibility to do that you think it is not actually going to be fit for? And for example, I know that some of the criticisms of blockchain are that it has very high energy use. It's got a relatively lower speed as compared to transaction speeds for like credit card transactions and things like that. And so does it scale? Can it scale up? Can it do some of the mass applications that it's being suggested for in your opinion? Jake, did we lose Jake?
Sorry, I'm here. I guess I was auto-muted. My apologies. Yes, so some of the criticisms or devil's advocate perspectives that you alluded to are certainly valid, I would think, with respect to Bitcoin. You know, the energy use of Bitcoin, the annual use of energy by the Bitcoin network is equivalent to that of some countries, the country of Ireland, for instance. And yes, scalability is a challenge. The average transaction time, the number of transactions per second for Bitcoin is about 7, whereas Visa does about 50,000. So there are barriers. But that is not to say that those aren't insurmountable. You know, there are other cryptocurrencies that have, blockchain-based projects that have looked to address some of those issues. But at the end of the day, I think the core idea behind many of these blockchains, which is the removal of the kind of independent third party, is really the crux. You know, the use cases that are going to succeed with blockchain are going to be the ones where that feature is critical. And you know, many of the use cases that blockchain is being touted for, in many cases, simply don't have that as a critical deliverable or a key feature that is a requirement. So you know that we don't have a great deal of time to dig deeper, but to me, that is the crucial aspect of this. In order for blockchain to be useful, it really needs to find a use case that dovetails with that distinct feature that blockchain offers, which is that separation out of the intermediary. The other aspect, of course, is that we're not really separating out an intermediary. We're not eliminating trust. We're just transferring trust to other players in the ecosystem. The people that write the software, the miners, the database designers, all those people. So it's not as easy as just saying, let's take out the middleman. It's more of a shift than an elimination.
Got it. Thank you. Given that, and that potentially there are other ways that this could be used, what are some of the innovations that you see potentially where blockchain could be effective? We've talked about, or I've seen, people talk about supply chain management, registrations for things like diamonds or land, even voting functions. Are these realistic use cases in your opinion? Are these things that blockchain would be effectively a good solution for, the best solution for, as opposed to the alternatives, things like that?
Look, I'm no arbiter on the future, success of these products. I do think at the end of the day, the market will drive a lot of this. Certainly, any blockchain solution has to pass muster in the real world. And there have been lots of organizations that have tried it and are looking at it, and we're still not clear on where it's all going to land. But to me, blockchain implementations which are highly scalable, which are efficient, which are not subject to the risks of being hacked, and we've seen lots of that, and also are used and administered in a context of effective regulation. I think there's a regulatory dimension to this space that's really been lacking and has driven a lot of the failures, in particularly in the cryptocurrency space.
So I want to get to one of the questions that was posed. You talked a little bit about permissioned and permissionless blockchains, and I know on permission, another word for that is obviously private blockchains, which can be set up within a set community, within an organization, a business, whatever the boundaries might be of the group who's engaged in that. One of the aspects of the public blockchain that has always been touted is the ability to stay anonymous as a user. And I know that that's been challenged in many cases. There's a lot of data to show that over time, patterns can be tracked, and even the relative anonymity of a particular user might be not as strong as was originally thought in terms of being able to identify who some of those users are. But on a private blockchain, is there any ability to remain anonymous within that community, or is by the definition of it being a managed private system that at least the system administrators and at least the other people involved know who you are?
Yeah, I think in a private blockchain, you're not going to have that anonymity feature. The anonymity feature has been really touted in the cryptocurrency space, and it kind of aligns with that desire to have a break from government and the establishment, the ability to transact financially without any strings attached, or any ability for someone to see what you're doing. So there really isn't any, at least in my mind, any kind of use case for having that anonymity present in a private blockchain. But look, I might be missing something there. But certainly on the public blockchain side, if we ever do get a cryptocurrency that is completely anonymous and persistently so, there are significant risks that flow from that. Can you imagine if organized crime was able to use that kind of cryptocurrency to transact completely anonymously, what that would mean for black markets, etc.
Thanks, that's a great point. There is one other question in the Q&A. If the person, I want to acknowledge that we got that question, but I'm going to defer that to the later Q&A because it specifically has to do with some banking and financial regulatory issues. And I think we'll be better placed to answer that and discuss that a little bit later. So let me ask one more question right now. Jake, one of the attributes about blockchains that again is touted as one of the benefits of it is the security, the fact that it's this hashed connection between blocks. It can't be changed. It can be verified. It's immutable is the word that's usually used for that. What are the privacy aspects of blockchain though that may or may not be as strong as the security attributes that it has? Because at least in the traditional Bitcoin uses, is my understanding, although it's very secure, it's also very public. The actual, even if the user behind the identifier is anonymous, the transactions themselves are public. Many of the aspects of what's happening are public, and that's not necessarily consistent with privacy, as well as the fact that keeping something immutable forever may in fact be antithetical to privacy as well, since one of the pillars of privacy is the ability to delete data or withdraw data from a system at some point of the user's choosing. So what are your thoughts about like the security versus privacy benefits of a blockchain system?
Right. So first of all, the Bitcoin, to use the example, Bitcoin blockchain is not an encrypted blockchain. You know, all the data in the blockchain is publicly viewable and accessible. The only thing that's encrypted in the sense of using an encryption function is the hash stuff that we've talked about previously. It's those use of those hash digests and hash functions, which is a cryptographic tool that is used to tie these blocks together. It doesn't offer any sort of cryptographic security beyond that. You know, the data isn't encrypted; it is publicly accessible, which raises the issue that you've mentioned. You're now creating an immutable permanent store of data, which could include potentially private information. How do you deal with that in the context of things like GDPR and other privacy rules that may exist? And you know, my colleague Matthias will dig into that deeper. But yes, it is a significant issue. I think as a whole, you know, security is in many realms becoming ever increasingly more important, and certainly, you know, some of the security that's now being wrapped around some of these blockchain implementations is meeting that challenge, I think. But yes, you're quite correct. The privacy issues, particularly if you start storing a lot more private information, or potentially private information, or information that combined with open source information or other data sets constitutes private information, poses a challenge. How do you manage that? You know, when there are obligations to delete, archive, change that information under applicable law.
Great, thank you. So there's one more question that has to do with investments, and again, I'm going to defer that to our discussion after we hear Matthias speak. But there is one other question I think if we can address very quickly right now would be appropriate. The distributed blockchains are often called immutable, as we were just discussing, but in reality, as you explained earlier, what it means is that over 50% of the nodes have concurred, which is then what locks it into the chain and makes it therefore immutable. Would this mean that if more than 50% of the nodes sort of colluded to make a change and then all agreed that the change was in fact now the accurate record, is that how, you know, you would sort of substitute a different history or a new truth for what was on the blockchain?
Yes, and that is the, you know, commonly referred to as the 51% attack. Now, the 51% attack, you know, it can't go very far back into the blockchain. You can appreciate that you might be able to go back a couple of blocks, but that still offers an opportunity for all sorts of fraudulent foolishness, and is a real risk. And there certainly have been instances of that happening in any of a number of blockchains. So it is a risk. Now, the other dimension of this is, you mentioned collusion. You know, it's not just actual collusion, but also, you know, the perceived reality, or the perception that flows from the reality that many of the miners, particularly for the Bitcoin blockchain, are large mining pools, which are controlled by the same individuals. You know, there are 2 or 3 major mining groups and mining farms that constitute, you know, 40–50% of the mining capacity. So that centralization, if you will, of that mining capacity is also a risk and a concern. But the reality, I think this is a problem that's certainly being studied and sought to be addressed. But it is a problem. I would think that it's very much one that focuses on the later transactions in a blockchain being at risk, and not the ones that have been confirmed weeks ago or months ago.
Got it. Thank you so much. Okay, I think we're going to wrap up this portion now. Jake, if you could flip to the break slide. Everyone, we're going to take a 5-minute break, and then we will come back and start back up again with our next session. So thank you for your attention thus far, and we look forward to seeing you in 5 minutes. Okay, Matthias, if you want to turn your video back on and
yes, give me 1 sec.
And I'll turn it back over to you.
Hopefully it works.
Looks good.
Can you see me?
Yep. Can see you and your slides, so it's all good.
All right, super. So we had some technical issues at the very beginning due to our wonderful IT setup of Deutsche Bank. So thank you very much for joining, and happy to be with you for the next 40 minutes. That is our agenda. Maybe Jake, would you please move on to the first slide of the agenda? Thanks. So I'd like to take you through the key cornerstones of data privacy in relation to blockchain. The key reference point of my presentation is certainly the GDPR, is the cutting-edge privacy law globally. It has influenced many other local privacy laws, such as the CCPA in California, and just to give you another example, the LGPD in Brazil. First of all, I think it's important to understand who the players are and how they interact in a blockchain environment. Then I will shed light on the relevant data subject rights with a focus on their factual enforceability. I will illustrate that one of the most striking work zones between blockchain and data protection laws is the compatibility of the principles of purpose limitation and data minimization with the blockchain finality principle. Please move on to the next slide, Jake. Yes. Further, we will showcase 2 techniques to reduce data protection risks when putting personal data onto the blockchain. It's worthwhile to have some thoughts on data privacy assessment and privacy by design in relation to blockchain. Last but not least, I will touch upon the most relevant legal grounds when processing personal data onto a blockchain, and after that I will open the floor for questions. Let's get started with the first slide here. Exactly, though, before diving in the roles of the blockchain players, I should know that data privacy laws around the globe have a quite common understanding of controllers and processors. Controller under the GDPR is a natural or legal person which, alone or jointly with others, determines the purposes and means of the processing of personal data. That's quite similar to the business under the regime of the CCPA in California, as a very advanced data privacy regime in the US. The processor under the GDPR is a natural or legal person which processes personal data on behalf of the controller. And that's very important, based on instructions issued by the controller on how to process the personal data provided to the processor. This is I see some similarities to the service provider under the CCPA. So we have huge overlaps, even though the details vary. So what are the roles of the blockchain players under the GDPR? The regulation sets out a predefined number, a very limited number of roles and responsibilities, such as controller, joint controller, and a processor, alongside data subjects. On the other hand, there are various actors in a blockchain environment which have a specific role to play. That comes down to the problem to what extent the roles defined in the GDPR may be associated to them, and if so, what does this mean in terms of accountability? So here are the players who interact with the blockchain network. The miners, nodes, wallets, users, developers of smart contracts, oracles, and governance bodies. So Jake exemplified some miners, some players here in his presentation. Let's dig in the details of those actors to scrutinize their relevance to the GDPR. So please move on to the next slide, the miners. What are miners doing? Mining is the act of solving a mathematical puzzle within the proof of consensus model. Jake just fleshed out what it is. Thus, miners validate transactions to be added to the blockchain. Miners are neither controllers nor processors, since they don't determine the specific purpose of the data processing operation. Neither do they carry out specific services based on instructions of the controller. They only belong to the blockchain infrastructure without taking over any role under the GDPR. It's worthwhile to note that the blockchain protocol itself doesn't include any instructions on how to process personal data written on a blockchain. Due to the lack of instructions, miners are pursuing their own purpose. They do it for more or less egoistic purposes. They want to earn money. They want to earn cryptocurrency in return after having validated the transactions. So please move on to the next slide. Nodes. Nodes are the decentralized computers that store a full copy of the blockchain. Once a miner finds a valid hash for the block, the node broadcasts its hash to other nodes, which subsequently run a computation to verify whether the hash is valid or not. In particular, whether it meets the specification of the protocol. And where this is the case, they add the new block to their own local copy of the ledger. Please note this is something which is done fully automatically without any human intervention. With that in mind, the node is simply a computer which cannot determine the means and the purpose of any particular data processing operation. Without any interference of a human being, nodes are running IT operation and hence only belong to the blockchain infrastructure as well. Please, next slide. Let's crack on what wallets are doing. Wallets are software packages at the application level designed to store and manage asymmetric key and addresses used for transactions. This is an official definition by the NIST. The NIST stands for National Institute of Standards and Technology in the US. Wallets allow blockchain users to control their own private key and, importantly to note, send transactions to the blockchain network, especially to the miners for validation purposes. Even though wallets may pass personal data to miners, it is evident that any data processing activity happens under the control of the blockchain participants who determine both means and purpose of the data transfer. The purpose is the creation of a new block containing personal data. The means is the usage of a specific blockchain application. In summary, wallets only belong to the blockchain infrastructure, unlike the other participants I just illustrated. They are neither processors nor controllers. Please, next slide. Let's move on to the users. That's a little bit more interesting. What are users doing? They participate in transactions run by a blockchain network. The CNIL, which is the French Data Protection Authority, and the EU Blockchain Observatory are jointly of the opinion that, in a nutshell, the users may act as controllers if they commit personal data to the blockchain, and most importantly, if this is done in conjunction with their particular business activity. By all means, you must consider the so-called household exemption pursuant to Article 2, Section 2C of the GDPR. According to that rule, the regulation does not apply, though the GDPR does not apply if a natural person processes personal data and if this activity has a private or familiar background only. That individual is not acting as a controller. For example, private correspondence or social network or online activities are performed for private reasons only and must be allocated to the household exemption. It's worthwhile to know that when assessing the household exemption, neither the size of the data being submitted to the blockchain nor the number of persons who might have access to the data on the blockchain are relevant criteria for assessing the applicability of the household exemption. So whenever that exemption applies, the GDPR has no relevance. And the users who submit personal data to the blockchain are not deemed to be controllers. Please, next slide, please. So the developers interact with the blockchain network. How do they achieve that? Blockchain applications often use smart contracts. A smart contract is a software, Jake made it crystal clear in his presentation, respectively an algorithm that once deployed to the blockchain can be executed without any interference from the developers. According to the CNIL, the French Data Protection Authority, the developers have no role under the GDPR unless they actively intervene in the particular data processing operation. That's the official guideline from the CNIL. Developers only provide a software solution to blockchain users who make use of it in order to perform a data processing activity onto the blockchain. The CNIL exemplified its view with the following use case, which is, I think, very, very clear. A software developer offers a software embedded in a smart contract to an airline in order to enable passengers to be automatically reimbursed when their flights have been cancelled or delayed. In that scenario, the airline would be the controller acting as a blockchain user. The developer simply provides the software to the user, to the airline, which capitalizes on the software, which benefits from the software. They are neither, so the developers are neither acting as controllers nor as processors. And that takes me to the next slide, the oracles. I think that's a very nice feature. And also from the legal point of view, very interesting. Oracles are external agents. I would call them agents that feed information into the blockchain network. That information is being processed through smart contracts. Oracles are used to process real-world events which occur externally, outside the blockchain. So this is a linkage between the artificial world of the blockchain and the real world outside the blockchain. Let's take the example with the airline and the reimbursement of the ticket costs. I just mentioned it before. The information that one flight has been delayed or cancelled is an event which happens outside the blockchain network, but must be considered in order to enable the smart contract algorithm to process that kind of information accordingly. Having that said, oracles have the task to transfer external data feeds or some sort of information to the blockchain to be digested therein. Oracles directly interfere in a data processing activity carried out by a smart contract algorithm. If one oracle does have a commercial interest in the outcome of this particular processing activity, the oracle should be considered as a controller or joint controller alongside blockchain participants, which make use of the smart contract. Please move on to the next slide. This leads me to the governance bodies. In a private blockchain, a governance body comprising of a group of legal or natural persons can be established to oversee and monitor blockchain transactions. This is only applicable to private blockchains. That body nominates a single point of contact for its network, which may determine the purpose and means of each processing activity. In that scenario, the governance body and its members are acting as processors and the single point of contact as a controller. If one group member is empowered to make decisions for the group, the appointed member qualifies as a controller according to the CNIL recommendation. One use case of governance bodies can be a syndicate of members of a supply chain. The members are acting as controllers and or processors. So please move on to the next slide. So how do data subjects' rights apply to the blockchain? The GDPR comes into play as soon as personal data is being processed. Important to note that submitting and storing data, personal data, onto the blockchain is considered as a processing activity, particularly with a view to the GDPR. If the storage can be linked to an individual / a natural person, the question will arise against whom the data subject may exercise these rights. It's of paramount importance to distinguish between private and public blockchains. In a private blockchain context, there are governance bodies, which I just said, in place, which are the perfect target to address any data subject rights. Opposed to private blockchains, public blockchains are much more problematic since the data subjects face two challenges from two sides. First, it's nearly impossible to clearly identify one controller whom the data right, the rights of the data subjects may be addressed to. And second, to force the controller once identified to perform his or her GDPR related duties, such as providing information or deleting personal information from the blockchain. So in a public blockchain context, this is very, very difficult. Please move on to the next slide. Let's have a look at 3 data subject rights, which impose a huge challenge for both the data subject itself and the controller. That is a right to access personal data, to rectify, and to erase data. These rights have a general meaning and are set out in various data privacy laws, even though the details vary in these jurisdictions, in all jurisdictions. But there's a general principle in place that natural persons shall have the right to demand access their data, to be informed what is happening with it. Further, they can claim the right to be forgotten. Nobody shall keep other people's data indefinitely. From the conceptual perspective, that right has a prominent footprint in many other laws, particularly in the GDPR, but also in the US. It clearly states that the data subject shall have the full control of his or her data and can request that the business or the controller deletes the data from its records under certain circumstances. Let's have a look at the right to access personal data. That right is a basic right. It's a prerequisite for the exercise of any of the other rights, such as deletion. Here's the issue. In a public blockchain environment, any controller is, as a matter of fact, not capable to fulfill his obligation vis-a-vis the data subject who is requesting the data access. This is because the data is typically encrypted or hashed, and it is impossible to decrypt the data without having the key under control. Irrespective of that, the controller is unable to identify that set of data which relates to the individual who was raising the request. The right to rectify personal data. That means that the individual shall have the right to request rectification of inaccurate or incomplete data which relates to him or her. That right clashes with the factual impossibility to modify any data given that the data is immutable once written onto the blockchain. Please move on to the next slide, please, which perfectly takes me to the right to erasure, the right to be forgotten. You must interpret erasure as a legal term very, very broadly. Erasure includes the overwriting of data or simply making it unusual. It's not only a matter of deletion, it's much broader. The ICO, which is a UK data protection authority, argued that any instances where data is being put beyond use can also be an appropriate method for erasure. Even anonymization can be a technique which may meet any deletion request. Unlike the request for rectification, it is at first glance not possible to delete data from the blockchain. However, I will showcase an alternative GDPR compliance solution in a little while when walking you through the options to meet such kind of requests. So bear with me. Next slide, please. And here you see that blockchain technology is apparently not in sync with the principles of data minimization and purpose limitation. Both principles are the backbones of any data protection laws worldwide. I will now elaborate on these principles in order to better illustrate the war zones between GDPR and blockchain. Next slide, please. So what does purpose limitation mean? Personal data shall only be processed for specific, explicit, and legitimate purposes. Any further processing shall not be permitted unless the data subject has consented to the new purpose. The rationale behind it is to prevent the use of personal data of individuals in a way they won't expect. It's very important to note. The same principle is enshrined in the CCPA and in many other local privacy laws in the US. So what does it mean in the blockchain context? Blockchain by nature continuously processes data, also in personal data, where applicable, as soon as submitted to the ledger. The issue is what happens if the data is not needed anymore? For example, after completing a particular transaction, or when a complaint issued by a data subject has been settled. Please remind just want to point you to the airline example. Or generally speaking, whenever the blockchain, whenever the processing activity has been completed. I call that kind of data legacy data. And I will get back on it shortly when we talk about data deletion. So in a nutshell, storing, respectively processing legacy data onto the blockchain is, in legal terms, not in line with the principle of purpose limitation. Please, next slide. This takes me to the next very important principle, the data minimization principle. It comprises two faults. First, there's a data quality aspect which partly overlaps with the purpose limitation principle. Only those data which is necessary to meet a given purpose must be gathered and processed. Second, and this is a timing aspect embedded in this principle, the period for which the data is being processed must be limited to a strict minimum. Two artifacts of the blockchain features are actually clashing with the data minimization principle. First, there is the ever-growing nature of blockchain. The personal data written on the blockchain is continuously mirrored in the subsequently added blocks. That inherently violates the data minimization principle. And second, personal data is being replicated in all wallets and computers around the globe, since all nodes have a full copy of the database. Please, next slide. Yeah. So what are the techniques in order to reduce any data protection issued as fleshed out before? In accordance with existing guidance from the CNIL, the French Data Protection Authority, I do recommend to check the following questions in that order. First question we have to keep in mind is it really necessary to put personal data onto the chain, to put personal data onto the blockchain? When the answer is yes, because this is part of your particular business case, you should determine the type of blockchain to be used. Private blockchains should be always the first choice, with a view to their governance structure, which facilitates to comply with data subject rights, as illustrated before. Irrespective of what kind of blockchain you are using, it is really critical to have state-of-the-art encryption techniques in place in order to safeguard the personal data submitted to the blockchain. Let's a little bit deep dive in the particular assessments on the following slide. And here I would like to jump to the third bullet, the usage of innovative encryption techniques, where I recommend to scrutinize the following aspects. First, anonymization should always be considered firstly. And why? It's clear, anonymization converts personal data to into non-personal data. As a consequence, the GDPR doesn't apply after getting the data anonymized. If this is not feasible, so if anonymization is not doable, you should use hashing techniques or at least state-of-the-art encryption. Please note that hashing is certainly one of the most effective techniques to encrypt data. But, and this is the flip side, hashing may not convert personal data into non-personal data. It only safeguards the data, but it's not changes the nature of the data. And that differentiates hashing from anonymization. Next slide, please. On this slide, on the next slide, I will be presenting two innovative techniques aiming to mitigate data protection risks, particularly to comply with data erasure requests and with the principles of purpose limitation and data minimization. Both techniques come down to the issue on how to handle legacy data. As mentioned before, legacy data is a set of data which is not needed anymore on a blockchain as a related transaction or a particular data processing activity has been completed and accomplished. However, the data remains on the blockchain. There are currently two remedies to be taken into account. One remedy boils down to setting up two or more blockchains which are closely intertwined. One blockchain is a private blockchain where the transaction or the real-time processing operation takes place. The other one, or the other ones, are public blockchains where the legacy data is being transferred to. As soon as there's no need to use personal data anymore onto the private blockchain, the data file is being removed from the private blockchain to put onto the public one, to park them on the public one. This technique makes both chains interoperable and may resolve the scalability problem. However, the legacy data is still visible on the public blockchain, where this data is being parked. Yeah? The usage of multi-layered blockchain, the setup of multiple of blockchains, is actually not the silver bullet on the journey for achieving GDPR compliance, as I just fleshed out before. But it's a great technical measure for safeguarding the data. And this takes me to the next slide, where I would like to present one technique which I think is the most straightforward and effective one in terms of resolving the described data protection issues around legacy data. I call it hashing out technique or mitigation measurement. Hashing out differs from the multi-layered approach, as a removed database is not being stored onto another blockchain. It is transferred off-chain to an external database. The original, respectively the reference data, is replaced with a hash which remains on the blockchain and points to the reference data which has been stored anywhere externally, in an Excel spreadsheet, a PowerPoint, wherever, but not on a blockchain. But here's the flip side. On the one chain hash, so the hash which has been put on the chain, I call it placeholder, remains on the blockchain. And please bear in mind that the hash value is deemed personal data. So on the next slide, I will show you how to tackle that issue. Slide 5, please. Next slide. Yeah. Yes, perfect. So let's have the example. If a natural person raises a request to erase his or her personal data from the blockchain, what needs to be done? The controller can meet that request by transferring the personal data off-chain, putting it out of the blockchain and deleting it anywhere else. Yeah, you have to transfer the personal data from the blockchain, transfer it externally and delete it there. The question is, what is happening with the hash value, which is still on the blockchain, as I mentioned before? The answer is that the hash is not, has nothing to relate to. After having deleted the reference data from the external database, the hash becomes a random string without any meaning. It's important to note that it is impossible to reverse engineer the reference data from the hash. Deleting the off-chain deleting the off-chain legacy or reference data from the external database has a huge impact on the hash value, which then converts into a non-personal data. In summary, the hashing out approach most likely complies with the principles of purpose limitation and data minimization, and is, from my point of view, currently the only measure to meet data erasure requests sufficiently. Because once you delete the original data, which has been stored externally, the hash value on the blockchain becomes a non-issue. It's a random string without any meaning and converts into a non-personal data. So please, next slide. On that slide, I will quickly lay out the requirements for the need to perform a data privacy impact assessment. I call it PR, privacy impact assessment. A PR is required if the data processing activity is likely to result in a high risk to the rights and freedoms of data subjects, and if a new technology is used. A new technology is certainly a blockchain technology. How to handle PRs? What are the controllers required to do? They need to carry out a balancing test. The controller must balance out his or her own interests against the interests of the data subjects concerned. On this slide, you may see the requirements when performing the balancing test. For example, an assessment of the risks data subjects may be exposed to. It's important to note that the PR must be carried out before starting the data processing operation. Please move on to the next slide. The privacy by design. It's an overarching principle of any data protection regimes around the globe, or the most important ones, that businesses adopt security measures which are appropriate to safeguard collected personal information. The details vary jurisdiction by jurisdiction. Under the GDPR, controllers must consider data protection principles and safeguards while it's stated in the recitals, developing, designing, selecting, and using applications, services, and products that are based on a processing of personal data. This is carried out by implementation of appropriate technical and organizational measures from the outset. So broadly speaking, the privacy by design principle requires controllers, businesses, or whatever you call them, to choose that kind of technology with the least impact on privacy rights of individuals. And this needs to be done from the outset, from the very beginning. Please move on to the next slide. As a consequence, the controller must at least encrypt data when submitting it to the blockchain. It's some sort of the technical organizational measures they need to implement. The optimal measure would be to hash the data as a state-of-the-art encryption technique. I have added two real-world use cases where you can see how data privacy by design or privacy by design and default works out. In the health sector, let's take this example. Doctors, patients, hospitals, and other healthcare providers can store health records in a blockchain environment or in a blockchain-based management system and grant access to records only to authorized parties. This model could stimulate business cases such as personalized medicine. In that context, it is critical that high-end security measures are baked in those kind of solutions in order to safeguard highly sensitive personal data such as health data. Another use case for implementing strong privacy mechanisms from the outset is Zcash. Zcash uses a zero-knowledge proof algorithm to verify the transaction without the need to disclose the identity of blockchain participants. Monero is another example of the blockchain-based network that obfuscates digital currency data, including transactional resources, by using advanced cryptography. While these approaches can help prevent re-identification of the blockchain users, it makes it more difficult for banks to perform their anti-money laundering requirements accordingly. The latter example may reveal that banks are more often between a rock and a hard place when adopting new technologies like blockchain. So next slide, please. And now I'm very close to end. The legal grounds under the GDPR. Just to set the scenes, in order to process personal data, irrespective of where the data is being stored, you must do it lawfully, fairly, and transparently. That is also a general rule which applies to all data privacy regimes. Under the regime of the GDPR, the processing must be based on one or more conditions specified in Article 6. Let's have a very quick look on the 3 relevant legal grounds in conjunction with blockchain. That's a contractual necessity. What does it mean? The data processing can be justified if it's necessary for the performance of a contract. I think smart contracts are the only use case where this legal ground may come into play. Consent, I think that's another very interesting topic. Consent, what does it mean? Data processing is legitimate when based on a given consent by a data subject for one or more specific purposes. There are some aspects to be considered in a blockchain environment. One issue is if you want to stick to the consent given by an individual, you must inform him or her about the details of the processing activity, such as the type of data being processed and for what purpose, from the very beginning. Second, consent in conjunction with blockchain can get pretty problematic in the case the consent is withdrawn, provided there is no other legal basis for the processing activity available. You must immediately stop the processing as soon as the data subject has withdrawn its consent. The problem is that the data is still stored on the blockchain, even though the consent has been withdrawn. There's nearly no way to stop the processing, the storage of the data being written onto the chain. With other words, the data processing continues irrespective of whether a valid consent is in place or not. This takes me to the last important legal ground, which is a legitimate interest. Processing of personal data is legitimate if it is necessary for the purpose of the legitimate interest pursued by a controller or by a third party. In practice, so legitimate interest is a one-trick pony. Controllers can rely upon when processing personal data. The downside is that they have to carry out and document a balancing test upfront, where they have to consider the competing interests of the parties involved. One prevailing interest is fraud prevention. In the case the banks want to utilize a blockchain-based solution, they can do it sticking to the legitimate interest as a legal ground, which makes the processing activity legitimate. So, and that's the last slide of my presentation. What are the takeaways? I would like to call out the most striking ones. There are still tensions between blockchain and data protection cornerstones, but they can be overcome by using smart and innovative techniques like hashing out. Moreover, you should watch out any guidances or recommendations from your local protection authorities, particularly from the European Data Protection Board. I know blockchain and data privacy is on the to-do list on the panel, or on the one of the to-do list of the Data Protection Board, but has not been prioritized yet. Recommendation issued by the data protection authorities would be binding, or particularly from the European Data Protection Board, would be binding for the other data protection authorities of the EU member states. I think this is something you should permanently look at. Then you can have a little bit more guidance on the usage of personal data on a blockchain environment. So that's that. Got 40 minutes. I'm just in time. Thanks a lot for your patience, and I would like to open the floor to questions.
Thank you, Matthias. Very much appreciate that very detailed and thorough discussion of sort of a use case, as it were, under GDPR of how blockchain works in this particular regulatory environment, as well as a lot of the other explanations of how things can and could work on blockchains. So I'd like to ask our other speakers to turn their videos back on now. I think mine may not be working, so I apologize if that's the case, but Rob and Jake, if you want to turn yours on, and then I'd like to turn this over to Rob to run the Q&A for a minute with some of the follow-on questions we have from the audience and some questions that I think we have as well.
Yes, thank you very much, Brenda and Jake and Matthias. Let's first run the questions that are still in the queue. And why do banks close accounts that receive withdrawals from crypto exchanges due to compliance reasons? So maybe one of you could.
I can attempt to answer that.
Yes.
There are in essence two primary reasons for that. The first revolves around anti-money laundering legislative requirements and obligations. If banks do not know where the money is coming from, who owns it, and what its purpose is, then they can't comply with their obligations under reporting legislation, like the FinCEN rules in the US, FinTrack in Canada, and legislation in other countries. Another reason may be compliance with sanctions legislation. Most Western countries have sanction rules that impose obligations on financial institutions to identify the holders of funds, et cetera. And if that's not clearly articulatable and reviewable, then they may run afoul of those rules as well. So it's really regulatory compliance in those two spaces that drives these kinds of decisions by banks and other financial institutions in most cases.
Well, thank you. Our follow-up question is from Vanita Peran. How does the investment industry implement a blockchain, and possibly some pros and cons on that?
I can do the first part, and if Matt wants to pipe up on the second, I'm happy to do that.
Yeah.
So in 2017, 2016 to about 2018, we saw a lot of use of blockchain with the view to creating an investment channel for people through ICOs, initial coin offerings. Literally hundreds of them, and they raised a significant amount of money at that time. So that is one means by which not the industry, but investment itself was sought from individual investors. The investment industry itself is doing a couple of things in this space. There are now some bond funds available that invest in either Bitcoin exclusively or in a basket of cryptocurrencies for investment purposes. We have a few in Canada that have been approved for that purpose. The Winklevoss twins in the US have a very large fund that they're trying to get compliant. And there is some interest from the investment industry to look at using blockchain for account management, trade management, transparency purposes. I know that in Australia there was a pilot by their exchange to in essence put stock trading on the blockchain. I'm not quite sure where it is. I've kind of lost track of where they are, but there certainly are some folks in the investment industry that are doing that. So Matthias, I don't know if you have any thoughts on the pros and cons of that. If not, I can.
Yeah, maybe I can give you my observation in terms of the use cases in the financial industry, not only related to investment, but financial industry in general. I think most institutions, particularly in Germany, they have been evaluating potential business cases for leveraging blockchain applications. And broadly speaking, I have observed that blockchain itself is not currently not the driver for establishing new business cases in the financial industry. However, it's a step-by-step approach, and after evaluating the business case, banks tend to perform so-called case studies, such as machine-to-machine payment applications, crypto fund depositories, or crypto fund management. But all of these scenarios are embedded and shrinked in case studies. So real-life applications are very rare. I have not seen too many of them. And just to give you an example, which is not related to investment industry, but there has been a very interesting proof of concept model. Some insurance companies and one public authority in Germany, they have recently created a private blockchain leveraging a smart contract in order to avoid multiple bookkeeping efforts. The smart contract was designed to calculate extra pay from the public authority and to optimize the amount of the premiums the customers have to pay. The smart contract algorithm was developed to consider these credentials, and it's worth to note that unmasked real-life personal data of the customers have been put onto the blockchain, only accessible to authenticated insurance companies. But the project has not left the proof of concept stage due to huge privacy concerns. Yeah, but I think all of these concerns can be tackled in anyhow, and it's only a matter of time where the use cases become real life or will be born in a real life scenario.
Thank you, Matthias. Let's move on to the next question. It's a little bit up in the chat, and I think it relates to on-chain data, but also to basically the household exception and to what extent it applies. So maybe you could say a few words on, you as a lawyer are most likely familiar with the Lindquist case, which basically was a decision by the Court of Justice of the European Court of Justice, and it held that referring to various persons on an internet page and identifying them either by name or by other means constitutes processing of personal data by automated means. Maybe say a few words to the on-chain data as a personal data and household exemption, please.
The household exception, it's enshrined in the GDPR, and it means whenever the household exception applies, there is the people who are putting personal data or their data onto the chain are considered as not controllers. The GDPR doesn't apply. You know? So there's a mismatch between household exemption and the applicability of the GDPR. Whenever the household exemption is applicable, the GDPR is out of scope. And the household exemption applies whenever personal data is put onto the blockchain or is being processed for only, broadly speaking, processed, irrespectively of where the data is being processed. But one prerequisite is that this should be done or is carried out only for private reasons or family reasons, but without commercial purpose. Because the rationale behind it is that the lawmakers wanted to scope out the usual people who are dealing with internet and blockchain or other things for their own environment, for their own pleasure, for their own purpose, without having a business case in mind, without doing it for commercial purposes.
Thank you very much. I mean, taking into account, you're talking to people with a non-technical background here. So you talked about hashing out and also on like on-chain data, and there's also the aspect of transactional linkability. So maybe you could clarify with an example in terms of privacy by design. How does that work? So to become compliant to the data protection principles and also consumer rights. How does that work? Maybe you can exemplify that a little bit more.
In relation to privacy by design, or?
Yes, yeah, privacy by design, and what is, if you, maybe you can rephrase, what does hashing out mean? How does it work?
Yeah, hashing out is a technique. Whenever you have personal data stored on a blockchain environment, and I think it only becomes relevant whenever a data subject wants to get his data deleted. Yeah, the data is there may be a very limited use case for the processing of personal data onto the chain. Let's have the example with the airline I just mentioned before. The airline example. Yeah, we have got a customer, of a passenger, whose flight has been cancelled, and he goes to Lufthansa. It's my favorite air carrier, and he wants to get money, reimbursement. And the smart contract algorithm checks via oracles. Okay, this guy here, he booked a flight, and the flight has been delayed, and here's the cash. The algorithm shells out the money to the passenger, to the natural person. So the complaint has been settled completely. There's no need to process the customer's personal data onto the blockchain, onto the smart contract anymore, because the complaint has been completed. So what can be done? What the airline who has set up this algorithm, who is using the smart contract, has to delete the personal data upon request. And one use case for this could be one use case for hashing out. So the bottom line is the personal data is being put beyond the use of the blockchain. It can be transferred to an external database, and the personal data of the customer concerned can be just transferred to an external database where the data is being deleted. But you have to use a hash or a placeholder just to have a link or linkage between the reference data, the original personal data of the customer, and whereas the data has been originally placed on the blockchain. This can be done by a hash point. The hash point is a personal data, but once you, or as soon as you delete the personal data externally on your Excel spreadsheet, the hash value becomes nothing. Yeah, it becomes a random string without no meaning, because there's no reference point to the original data which has been deleted. And in this case, and this is according to my personal opinion, the hash value becomes a non-personal data, yeah, or can be converts into non-personal data. And this is meant by hashing out.
So if I summarize correctly, you're breaking the link between the transaction information that is on the blockchain and
Yes.
the personal information that's kept off blockchain in a separate database. Yes.
Yeah.
That's interesting because I always also looked, and maybe most of you have read in the news about the data breach in Finland, which consisted also the leakage of social security numbers. And in Finland, they're looking at replacing around 40,000 social security numbers, which is quite a staggering amount. If I hear you correctly, it would not be wise to store those directly on the blockchain in a readable form, and possibly also not in a hashed form. It would be more wise to, because in Finland, the social security number is used as the linking identifier for many different systems, interconnected systems, to keep those off the blockchain. Is that correct?
Yes.
Yeah.
Interesting.
One nuance for that, Rob, is as well that, if you store hashes on the blockchain, and the hashes are of data that is tightly structured. In other words, this is a 9-digit number and it's separately hashed. You can use a brute force attack to, in essence, generate all hashes for the corpus that you're dealing with. So in other words, for social insurance numbers, you could generate all the potential hashes and then just match backward from the hashes to the original numbers, and that way identify that data, which is how data breach work when they find your password. Most of the times, passwords are stored in a hash format, but if you know what the structure of the data is, you can, in essence, brute force all of them and then reverse engineer them backwards. So that's the risk.
I have another question in the queue from Maria Villa, and it sees also basically to the difference between a private and a public blockchain. And is it possible to convert a private blockchain to a public one and vice versa? Maybe you can say something to that question.
I'm not sure what she means by convert. I mean, you could certainly connect two blockchains together through protocols that enable the persistence of the immutability of both chains using, double pegs and mechanisms like that. In essence, locking in the state of a particular, item on the blockchain and then unlocking it after changes from the secondary blockchain have been made. Theoretically, I suppose you could take a public blockchain and convert it into a private blockchain. It would mean reconfiguring the software that is being used and how you go about confirming transactions or whatever attributes of the old blockchain you want to change in the new chain. Not impossible, but I'm not quite sure. Perhaps I'm misunderstanding the question. I don't know, Matthias, if you have anything to add to that or a different perspective.
I think the only way you can put both chains together is using a multi-layered blockchain where you can make both chains, private and public one, interoperable. But I think I'm not sure whether it's possible to turn public blockchain into a private one, because you have to redesign, to recode the blockchain protocol. Do you have any idea, Jake, if that is technically possible? I think technically is everything possible, but I think it wouldn't make sense.
You mean if you fork the chain, and a fork is just a way to update the software, you could theoretically change anything in the blockchain you like, including the consensus mechanism, the proof of work or other mechanism timing or considerations. Yeah, so you could convert them, I suppose, but I'm not quite sure that I appreciate the rationale for that. So apologies for not being more enlightened on this question.
Right, I have another question from Daniel Arin. It's a little bit complicated, but maybe I can rephrase it a little bit because I think it sees to my data spaces. It's like more like the individual control about your data. So given a proposed system where the data subjects have their own personal encrypted data repository, and they use a data wallet in order to give access to a third party in a peer-to-peer model, which allows the data subject to revoke access and consent. So like total control over the data space itself in the blockchain. The legal question then is, would this approach reverse the roles of the data processor in the sense that we give the user the power to decide who they share their data with and make the user basically his own data processor? Maybe Matthias, this is maybe enlightens some additional thoughts there.
you think, if I understood correctly, the bottom line, if it's possible to treat data subjects as their own controllers, is that the essence of the question?
Yes, the essence is that you have a data store, blockchain based, with health data, financial data, all types of personal data, where you have access to which parties, you have access about the control to which parties you share this. And where, if so, does that then change the roles in terms of GDPR interpretation of control and process?
This is a very good question, because this one has been discussed in a paper issued by the European Parliament, the research service of the European Parliament. I think from the rationale why or just to enforce the rights of data subjects, it makes no sense to enable them to act, to treat the data subject as their controllers. Otherwise, the rights or the enforcement would not be possible if data subjects are treated as controllers. Though you need a two-party scenario where the data subjects, they can raise particular subjects against the controllers, and they have to meet, the controllers have to meet the subject, the data subject rights requests, such as deletion or having access to the personal data. So if you match both roles, subject and controller, into one single entity, the rights would be flown into the nirvana, because there's nobody who can meet or comply with the data subject right requests.
Thank you very much. I think I learned a lot during this 2 hours. What we're going to do is I'm going to hand it back to Brenda. And before I do that, I already want to thank you, Matthias, and Jake, for this great masterclass. Thank you very much.
You're welcome. Pleasure.
Thank you, Rob. Thank you, Jake and Matthias. That was really, really fascinating. I thought that I knew a lot about blockchain already, but I have learned so much today, and hopefully everyone else engaging with us has as well. Thank you all for your participation and attendance today. Just want to reemphasize that the video recording of this session and the slides from the class will be posted at fpf.org/classes, probably in about a week, but please just keep checking there. You can also find there materials from all of our previous classes and sign up for the email listserv if you are interested in future sessions. This does wrap up our 8-part masterclass series, but we will be having specific one-off classes in the future on particular technical issues. And in fact, we already have one tentatively scheduled for December 9th that is going to be an in-depth look at supervised and unsupervised learning in AI systems, machine learning-based systems. So we already had a sort of AI 101 masterclass. This will be sort of a more detailed, more technical class, tentatively for December 9th. So please keep an eye out for registration and on the website. And thank you all very much for your time and attention today. Thanks one last time to all of our speakers.